All endeavors of mankind need energy. The most convenient form of energy is electricity. Electrical energy can be generated by burning coal or oil in a thermal power plant. Or it can be generated by exploiting the potential of falling water in hydro plants. It can also be generated from the energy of atomic fission in a nuclear power plant. The tremendous potential of nuclear energy in India was visualized by Dr. Homi Jahangir Bhabha way back in 1944. Thanks to Dr. Bhabha's foresight, from a humble industrial background, today we are self-reliant in this advanced technology. Several nuclear power stations are in operation or under construction. We are designing and engineering our own atomic power stations. The embryo of this program was conceived with the founding of the Tata Institute of Fundamental Research at Bombay in 1945. In 1948, the Indian Atomic Energy Commission was set up. The assignments were to survey the country for atomic minerals and develop their processing on an industrial scale, and to set up laboratories and initiate research on peaceful uses of atomic energy. These activities grew when in 1954 they were centralized into the newly created Atomic Energy Establishment at Trombay, Bombay, now called the Bhabha Atomic Research Center, in short BARC. It is our national center for research development and training in the field of nuclear energy. The early research facilities at BRC included Apsara, India's first research reactor built in 1956. Since then, the swimming pool type reactor is being used for experiments and also for production of radioisotopes. Cyrus was the next reactor to come up at the center in 1960. This reactor, meant for research, testing and training purposes, was built with Canadian assistance. It is fueled by natural uranium, moderated by heavy water, and works up to a power level of 40 megawatts thermal. Zarlina, the third reactor in the series, was built in 1961, mainly for reactor physics experiments. The Atomic Fuels Division of the Center was set up to develop the technology of fabrication of reactor fuel elements. This division also produces fuel elements for Cyrus. Electricity from nuclear energy was generated for the first time in India in October 1969 with the commissioning of the Tarapur Atomic Power Station, 100 kilometers from Bombay. This station, designed, commissioned and constructed by the International General Electric Company of USA, has two boiling water type reactors. It uses around 2.5% enriched uranium as fuel. Tarapur, being far away from coal fields, is an ideal location for a nuclear power station. The station has a generating capacity of 420 megawatts of electricity, which is fed into the grids of Maharashtra and Gujarat. India's second nuclear power station, the Rajasthan Atomic Power Station, is at Rana Pratap Sagar, 64 kilometers from Kota. This station has two pressurized heavy water type reactors having a total capacity of 440 megawatts of electricity. The first unit started feeding power to the Rajasthan grid in April 1973. These reactors were built with Canadian collaboration and use natural uranium as fuel and heavy water as coolant. In 1967, while RAPP was under construction, several more nuclear power plants of the same type were planned. For centralized management of all these projects, a new division was created in the Department of Atomic Energy. This division, called the Power Projects Engineering Division, or PPED, looks after all aspects of nuclear power projects, including design, development, procurement, planning, fabrication, construction, erection, commissioning and operation. The ancient rock-cut temples of Mahabalipuram, 80 kilometers from Madras, bear witness to our cultural heritage. Just next to it, we have our third atomic power station, called the Madras Atomic Power Station. Here, two pressurized heavy water reactor units of 235 megawatts each are in an advanced stage of construction. This station incorporates several new features compared to the Rajasthan station. Notable among these are the pre-stressed concrete containment, submarine tunnel for drawing cooling water from the sea, and a closed indoor switchyard. Our fourth atomic power station at Narora in western UP is under construction. This station will also have two pressurized heavy water reactor units of 235 megawatts each. The station incorporates several improved design features, including the ability to withstand earthquakes. The Madras and the Narora power projects mark the coming of the age of the Indian Atomic Energy Program, as the entire responsibility of design, construction and operation of these power reactors rest with Indian scientists and engineers. Over the years, there has been a significant increase in the indigenous content in terms of both know-how and components manufactured. Design work has already been initiated in Power Projects Engineering Division for the larger reactors of 500 megawatts. These reactors will incorporate many original features, as also some features which are being tried out in Narora. To sustain our ambitious nuclear power program, we have been building up a network of industrial complexes catering to the specialized needs of the nuclear power industry. For example, take fuel. This is a fuel bundle used in our pressurized heavy water reactors. It contains 15.2 kilograms of natural uranium dioxide encased in zinc alloy tubes. One reactor carries 3,672 such bundles, which works out to 56 tons of uranium dioxide. Annual requirements per reactor are 2,000 bundles or 30 tons of uranium dioxide. These requirements are met from uranium mines in Bihar. After mining, the ore is processed and sent to the nuclear fuel complex at Hyderabad. Here, the ore is further processed and converted into uranium dioxide powder. This powder is then compacted into pellets by powder metallurgy techniques. The pellets are loaded into tubes of zinc alloy, which are then sealed. 19 such sealed tubes are assembled to form a fuel bundle. The nuclear fuel complex also fabricates the enriched uranium fuel element for Tarapur. For this, enriched uranium is obtained from abroad. Another important function of the nuclear fuel complex is production of zirconium metal sponge and fabrication of zirc alloy components. The raw material for zirconium is zircon sand, received from the works of the Indian Rare Earths Limited in Tamil Nadu and Kerala. In the zirconium oxide plant of the nuclear fuel complex, the zircon sand is fused, leached, purified and calcined to get zirconium oxide. In the zirconium sponge plant, this oxide is mixed with carbon. And subjected to several metallurgical processes. To obtain the reactor-grade zirconium metal sponge of high purity. The zirconium sponge is alloyed, compacted, melted in vacuum arc furnace and cast into ingots, which are fashioned through rolling, extrusion, welding, and pilgering to various reactor components like cladding tubes, calandria tubes and coolant tubes. The nuclear fuel complex today constitutes an important infrastructure of our nuclear power program. Our power reactors require heavy water for use as moderator and coolant. Each reactor of the Rajasthan type needs initially about 200 tons of heavy water. This requirement was foreseen as early as 1962, when a heavy water plant of 14 tons annual capacity was set up in Nangal, Punjab. More recently, 4 more heavy water plants have been coming up at Kota, Baroda, Tuticorin and Talcher. Together they will have an annual production capacity of 300 tons of heavy water. This is the control room of a nuclear power plant. A nuclear power plant requires extensive electronic controls and instrumentation. The Electronics Corporation of India Limited at Hyderabad meets our specialized requirements in electronics. It makes instrumentation and control panels for our power reactors. It also manufactures radiation monitoring instruments and electronic computers. The myriad of components required in a nuclear power plant are supplied by various manufacturers and fabricators from all over the country, both in private and public sector. They have developed the specialized skills to meet the exacting standards required for executing jobs for the nuclear industry. Indian manufacturers now have the capability to fabricate components like cylindria, end shields, steam generators, heat exchangers and other process equipment. An indigenous nuclear power industry requires a strong base of research and development. This is provided by BRC at Trombay. We have already seen the Atomic Fuels Division, which helped in developing fuel fabrication technology, and the research reactors Apsara, Cyrus and Zerlina. Other facilities at BRC include the Reactor Engineering Division, which conducts engineering research, development and testing work. For example, this is an experimental boiling water loop for basic heat transfer studies for nuclear reactors. This is the fueling machine for one of our power stations, being tested at Reactor Engineering Division before being shipped into site. The Experimental Stress Analysis Laboratory of RED solves engineering design problems. BRC also has a central workshop. It handles specialized and intricate jobs which others would not undertake. The only nuclear fuel which is available in nature is uranium. It so happens that India has limited reserves of uranium. However, we have vast quantities of another material, thorium, which can be converted artificially into uranium-233, a nuclear fuel. Most of our thorium deposits occur in the form of monazite in the beach sands of Chavara in Kerala and Manavala Kuruchi in Tamil Nadu. These sands are processed by the Indian Rare Earths Limited for separating out monazite, zircon and other minerals containing rare earths for commercial applications. The monazite is chemically processed by the Indian rare earths to get reactor-grade thorium oxide. The conversion of thorium into uranium-233 can however be done only in a nuclear reactor. Thus, to be able to utilize our enormous thorium resources for power production, we have chalked out a long-term strategy. This consists of 3 stages. In the first stage, heavy water reactors are being set up with natural uranium as fuel. These serve a dual purpose, producing power and at the same time converting some of the uranium-238 to fissile plutonium-239. The plutonium from these reactors would be used as fuel in the second stage in fast reactors. Thorium will be fed in these fast reactors to convert it to fissile isotope uranium-233. The reactors in the third stage will mainly be based on the thorium-232 uranium-233 cycle and therefore would need to be fed only on thorium. The 3 stages are consecutive and to go from one to another will need several years of operation. Our current pressurized heavy water reactors, which include Rajasthan, Madras and Narora, represent the first stage of this strategy. While the first stage is successfully underway, we have already taken the initial steps towards the second stage, that is the plutonium-fueled fast breeder reactors. A new complex called the Reactor Research Center, responsible for developing the know-how and technology for fast breeder reactors, is coming up at Kalpakkam, alongside the Madras Atomic Power Station. At this center, a 13 megawatt fast breeder test reactor is in an advanced stage of construction. The center also includes several laboratories for research in fast breeder reactors. In a country with millions of poor, with many villages still without electrification, many places remote from coal fields, far away from hydel sources, electricity from nuclear energy will work wonders.